Okay, so today we're going to try and solve these equations, and basically you're not really using a calculator to get the answers, but you can check all of them on a calculator by doing this. Take the left side of your equation and enter that as y1 on your calculator. And y2 is the right side, like that. And you can graph these and see where they cross. Okay? So they look like this or whatever. And you can see where they cross. They cross, you know, at 3, 1/2 or whatever. I don't know if it's 1/2. It's just 3, something. It's actually 3, 1 point something. Okay? But the point is, you could easily get that intersection point because you guys know how to use the intersect button on your calculator. I hope you do. And in AP Calculus, when you guys take that class, you're expected to solve problems this way sometimes. Like during the AP exam, you're actually supposed to graph both sides and see where they cross. That's pretty common. So anyway, you need to know that. Obviously, we can't do that on a test, so all these problems have to be solved by hand. But this is a great way to verify the answer, you know, use the calculator. Okay, so let's do this by hand. So let's just review real quickly the rules that we learned on Friday. So one of the rules we learned is that if you have log base b of mn, this can split up into log base b of m plus log base b of n. And if we have, so that's one rule, if we have log base b of m over n, it becomes a difference of logs. So like a subtraction situation. Give it 1 second. Okay, so you have log base b of m over n, fraction makes a subtraction, right? And I think this was not new for anyone. So these are two very important rules. And then there's actually a third rule, and that was if you have basically log base b of m to a power, you can bring that power to the front. Like that. And that one actually is one of the ones we use the most. So, because it works on even a problem that only has one log in it. Well, anyway, let's look at this problem that we have here. Some people would look at this and say, oh, I'll just cross out the 2 logs. Why not? So they'll go like this. Bam, bam, and they'll just get 2x equals 9. This is the wrong approach. Okay? It's the wrong approach. You cannot just cross out the logs like that. The goal is to cross out the logs, but not quite yet. So does anyone know what we need to do first on this actually? Yeah, you can't have this 2 in the front when you cross out the logs. Okay? Let me erase my calculator solution so you can see this. Basically, we need to take this 2 and move it up to here, see? And then it looks like, here's the correct approach. It looks like log base 5 of x squared equals log base 5 of 9. Then you cross out the logs, see? So you end up with x squared equals 9. Okay, so what is the solution to this problem? Okay, plus or minus 3, but logs are finicky creatures, and they will only eat certain numbers. Okay? So we just have to be really careful. Sometimes we keep both of these answers, sometimes we don't keep them. The only way to really know is to go back to the beginning and plug in the answers. Okay? So let's go ahead and check. Let's do a little check here. If I write 2 log base 5 of 3 equals log base 5 of 9, this is a perfectly true statement. But if I write 2 log base 5 of negative 3 equals log base 5 of 9, this is actually not true. So this one's true. This one's not true. Why? And the reason is a log will not accept a negative input like that. See? So we don't allow that. So at the top of your paper, I would like you to write this. Log, and then draw a little box right here. Okay, and in the box, I'll show you, write positive, but not 1. And then in this part, write positive. So what this means is the base cannot be 1. It's a positive number, but it cannot be 1. And then the argument of the log, that's the part after the g, that can never be negative. So basically, that's why we can't have this -3 here. The domain of a logarithm is strictly positives. Okay, so we're going to actually go with 3 only on this answer. X equals 3 only. And you can be 100% sure that my test, you will be throwing away certain answers and keeping certain answers, because that's important to me. Okay, can we erase this first example? All right. Let's erase that. Let's go on to next one. Okay, so here are 3 rules of logs. So on this problem, you can actually exercise the second rule, because you see 2 added logarithms, see? So you could actually collapse those into 1 log. So I'm just going to use the second rule of logs. It was actually the first one on yesterday's notes, Friday's notes. But you could just write this as log base 4, and then multiply the x plus 3 and the 2 minus x like that. Okay? So you basically have log base 4 of negative x squared minus x plus 6 equals 1. And then you have to get rid of the log somehow. So you can bring you can think of it as 4 to the first equals negative x squared minus x minus 6, or plus 6. So you could just basically move that 4 over and bump that 1 up into the power realm. And then this one solves. If you bring everything to the right side, you get x squared plus x minus 2 equals 0. In other words, if you factor it, it's x plus 2, x minus 1. Okay, so this one has 2 answers. X equals negative 2, and x equals positive 1. Okay, so we should check them, right? Because we do have these finicky creatures called logs. So how do we check them? Just plug them back in. Where do you plug them in? The very, very beginning, right? Before you did anything to the problem, you have to use that, okay? So let's plug in the negative 2. So we're checking. Is it true that log base 4 of negative 2 plus 3 plus log base 4 of 2 minus negative 2 is 1? The answer is yes. This gives us log base 4 of 1 plus log base 4 of 4 equals 1. This is actually a true statement, because what is log base 4 of 1? What power of 4 makes 1? The 0th power. And what power of 4 makes 4? The first power, right? So this gives you a true statement. And if you try plugging in the x equals 1, it works as well. So I'll just write down, I plugged in x equals negative 2, and it worked. Why don't you guys try plugging in positive 1 and see if it works, okay? Go ahead and do that. Plug in x equals 1. Okay, so this time you just basically get 1 plus 0 equals 1, and that works too, doesn't it? So if you plug in 1, you have log base 4 of 4 plus log base 4 of 1, and this is just 1 plus 0 equals 1, which is true. So both of these work. And so we say they're not really extraneous roots, right? Those work. Okay, let's go on to the third example. Can I erase the ink? Okay, so for the third example, you'll notice I would like to join these 2 logs together like I did on example 2, but I have 2 different bases. So that's not going to work out too good. So what I need to do is rewrite these so they have the same base. Okay, so what I'm going to do is I'm going to go ahead and change this to a log base 2. So here's how we do that. I'm going to leave the first term as log base 2 x plus 3, but But the next one I'm going to write it as log x over log 4, and I get to pick whatever base I want. So I'm planning on using base 2 because that's the way the first term was. So I'm going to put in a little 2 right here and here. So I just rewrote log base 4 of x as log 2x over log 2 4. And the right side is just a 2, right? Okay, and then look right here. This is a number, isn't it? What is log base 2 of 4? What power of 2 makes 4? 2. Okay, so that is just a big fat 2 right there. This is just a 2. And I don't like fractions, so let's just double everything. So this problem looks like this. 2 log base 2 of x plus 3 plus log base 2 of x equals 2. And then we would like to join the logs now. They do have the same base, but we can't quite yet. Sorry, yes, making sure you're awake there. The right side's 4. Thank you. I'm supposed to multiply everything by 2, including the right side. Notice I have the same base logs, and so I can join these logs. First I need to move this 2 up to here. Move here. Right? That says move here. Okay, so it's basically log base 2 of x plus 3 squared plus log base 2 of x equals 4, and now you can collapse it into one logarithm. So it's log base 2 of, and this would be x squared plus 6x plus 9, but you're multiplying by x. So it's x cubed plus 6x squared plus 9x once it's all collapsed. Okay, we're very close to done on this problem. We have to now get rid of the log. So we can accomplish that by just inverting this and writing 2 to the 4th equals x cubed plus 6x squared plus 9x. So I'm going to show my work up here now. So it's x cubed plus 6x squared plus 9x equals 16. So bring everything to one side. Oh my goodness, P's and Q's? Really? Yes, really. P's and Q's is not something you just learn, it's something you use when you need it. It's a tool, okay? Fortunately, I can tell you one of the roots right now. Look at the equation. What number, when plugged in, gives us 0? 16 minus 16, can you guess the number? It's not 2. Nope. It's 1. 1 cubed plus 6 times 1 squared plus 9 times 1 is 16. So 1 is a root. X equals 1 is a root. You can just tell by inspection. Just look at the problem. And therefore, I can do synthetic division to break it down further. I already know that 1 is a root, or a 0, you could say. Okay, so I'm going to put 0. I think that's actually the correct terminology. 1 is a 0. Okay, let's go ahead and try this synthetic division. Okay, so I'm left with this quadratic, x squared plus 7x plus 16. But that thing, unfortunately, doesn't have any real roots. If you try to solve it, x equals negative 7 plus or minus square root of 49 minus 64. Discriminant's negative, so I don't care what it's over. Look, this is going to give us imaginaries, right? So I think x equals 1 is the only answer to this problem. See?
So you don't find the imaginary roots?
No, you don't give the imaginary solutions. That's a good question. Okay, so let's talk about that for a second. Remember, these x's, right, are supposed to go back into the original problem. So right now, if you plug in x equals 1, that's all perfectly legitimate. But it would actually be incorrect to plug an imaginary number into these. We're working with real logarithms here. So it wouldn't make sense to even use I in this context because we're studying the log graphs. We said the domain is positive real numbers, right? Okay, so there you have it. So x equals 1 only. This is just a dead end. This part. X equals 1 only. Okay, so that's kind of a harder example, wasn't it? The different bases makes it really hard to work with. You will find that when you do the homework for this page, which is actually due Thursday, you should be able to go through the notes and pick an example that looks most like the one you're working on, because I'm doing 8 examples today, so it will definitely be wise to have your homework handy. I'm sorry, your notes handy while you're doing homework. Okay, let's talk about some other different varieties of problems. Like this next one looks nothing like the others, but we should still know how to solve for x. So you know what this reminds me of is this looks to me kind of like a quadratic, you know? Like if you are given something like this, it looks like this to me. It's got 3 terms. 4 to the x is just the square of 2 to the x. So this is just the square of that. So this looks kind of like this situation to me. You see that? It's almost the same exact thing. So what I'm going to do is remind myself how I would solve this one. In order to solve this, I would try to factor it. I would need an m and another m to make the m squared. So that would be my first objective, to get the m, right? M squared. And then I would try to keep two numbers that multiply to make negative 12. And so, you know, you might come up with 6 and, you know, negative 6 and positive 2, but that's not quite right because the middle term doesn't work. So then you play around with it and you put in, you know, negative 4 and 3, and then you're like, oh, I got it. This factors, right? Well, this problem that I gave you also factors. It just looks a little bit different. It actually factors into 2 to the x minus 4 times 2 to the x plus 3, like that. This actually factors. So I'd like you to take a moment. I'm going to pause the recording. I'd like you to FOIL that and be sure that I really factored it correctly. Okay. So it FOILs properly. 2 to the x times 2 to the x is 2 to the 2x. So those are your firsts. Your outers, you have 2 to the x times 3, so the best you can do is write it like that maybe. The inners in your FOIL looks like negative 4 times 2 to the x. And then the lasts in your FOIL are negative 4 times 3. And then these two terms actually do form negative 1 times 2 to the x. You know, if you have 3 happy faces minus 4 happy faces, what do you have? Negative 1, what? Happy face, right. So if you have 3 2 to the x's and you take away 4 2 to the x's, you're left with negative 1 2 to the x's, aren't you? Okay, so this is definitely factored correctly, and now we solve it. So the zero product property states that 2x minus 4 equals 0, or 2 to the x plus 3 equals 0. So 2 to the x minus 4 equals 0, or 2 to the x plus 3 equals 0. So write that. And now let's solve it. So you add 4 over. And you can tell the answer is obviously x equals what? 2. This one you subtract the 3 over. And this is something my calculus students would know right away. They would look at this and say, that has no solution. And if you ask them why, they'll say an exponential has a positive range. They too have drawn a flashcard of 2 to the x, or at least in their notes several times, and they know this can't give out negative 3. Negative 3 is down here. How can this ever be? So this is a dead end right here, this part. But we did get x equals 2 as a solution. So this problem is very, very different from the others, but it looks quadratic in its format, and that's why we decided to factor it. Even if it wouldn't factor, I would have used the quadratic formula, as you'll see in example 8. Okay, let's go on to the next one. Can I erase the ink? Except I just clicked settings. So I'm waiting for a new menu to pop up all of a sudden. Okay, let's go to example 5. This is a short one. I think I skipped one. 5 and 6 are both short examples. So I thought I'd show you different ways people think about these. So we've actually solved this problem before, but it wasn't written like this. On Friday, I asked you to find log base 2 of 5. This is actually the same question. Okay? Log base 2 of 5 means what power of 2 makes 5. And 2 to the x equals 5 means what power of 2 makes 5. Right? So some people just look at this and they're like, oh, an exponential base 2. I'll just write a log base 2 on the other side. These people are done. There's nothing to do. They just understood the question and they rewrote it as a log statement. And if they wanted to get their calculator, 2.32. Okay? Another student might not be so savvy and just say, well, I need a method. Give me a method. How do I solve this? Well, you can actually solve this by putting a log on each side. So put a log on the left side and simultaneously a log on the right side. I mean, we feel comfortable crossing out logs, so we should feel comfortable putting logs in whenever we wish. So see the red log? I just added that. I'm using ln. You can use log if you prefer. And what does this do? This allows me the privilege of bringing the x out to the front, which is nice because now it's no longer a power. And now I can solve it by division. So x is ln 5 over ln 2. Same thing as log base 2 of 5. Still 2.32. Okay, then the third method would be, some people look at it this way. They'll say, oh, 2 to the x equals 5. I would like to undo the 2 to the x. So they're going to pick a log and probably going to pick log base 2. So they'll log base 2 both sides like this. They'll take this equation and they'll put a little log base 2 right here and log base 2 right here. What does this accomplish? This cancels out. It's all the same thing, but my point is there's different ways of thinking about it. The first student is just understanding the question and writing it as a log. The second student is actually applying a method where they put an ln into the problem. Okay? The third student is being a little more careful and using a log base 2 and putting that into the problem. And it inverts this. So this is a more mechanical approach. This is a more understanding approach. And then there's the student who graphs on the calculator and tries to guess what x is. Okay? After all, this does have a solution, right? We believe, according to the intermediate value theorem, that 2 to the x, since it passes from the point 2, 4 to eventually reach the point 3, 8, we believe that it has to pass through 5 during that journey. If it's going to rise from 4 to 8, it has to pass through y equals 5 somewhere in between. That's the intermediate value theorem. So we know there's an answer. So some students would just graph on the calculator and try to find the intersection point. Okay? And I think you should do that after you're done with the problem. Okay, let's go on to the next one. This one's the same problem in disguise if you divide by 8 first. And you kind of have to divide by 8. But now you have 3 to the x equals 5/8. And then I'm just going to use the sort of the middle of the road method, method 2 for my last problem. I'm just going to put an ln on both sides. Like that. And this allows me to bring my x out to the front. And then I can divide. Okay, now let's say that you're taking a test and it happens to be multiple choice. And you just got your answer and you're very proud of it, and you circle it. But then you look over at your answer choices and you see stuff like this. Well, the answer is B. Okay? Let's talk about this for a minute. So we know that this can be written as ln of 5 minus ln of 8. See? So there's many ways of expressing these answers. So one student might say ln 5/8. Another student might say, no, ln 5 minus ln 8. See? Over ln 3. They're both right. The same thing. Another student might say, don't write ln 8. 8 is 2 cubed. This is 2 to the third. Why would you write 8 there? Don't do that. So they might write it like this, ln 5 minus 3 ln 2 over ln 3. All of these students are correct. All of these answers are exactly the same. So you have to be very, very flexible when you look in the back of the book. Your answer might look different from theirs. In fact, I can think of another way to write it. Here's a third way to write it, or a fourth, I suppose. ln 5/8 over ln 3 can be written as log base 3 of 5/8. That has its advantages. Look how simple it looks. One single logarithm. One single base. You know, it's hard to decide which is the best answer here. And if you're taking a multiple choice test, from me, you need to be very flexible with your answer. Yeah. I know. There's an infinite number of ways to do this. So we have to be careful not to assume we're wrong when we're right. Okay. Let's go ahead and clear that ink, and let's go to the next one. Okay. Let's go ahead and put a log on both sides of this one. The reason is we don't like the fact that x is our power. That makes the problem awkward and new looking. Let's put the phones away. I should just check my messages. I'm going to check my messages real quick. I'm going to update my Facebook status. Hold on. I already wished him happy birthday. So okay, let's see. Update Facebook status. Status. What should I put? Math rocks. Math rocks. Why do students sleep in class? No, I won't put that. Why? Math rocks. I'll just put math rocks. Math rocks and rules. Math rocks and rules. All right, there. Oh, sorry. Did I distract you? Okay. So how do you solve this? Well, the fact that the x's in the powers is the annoyance here, right? So now we have a way we can fix that. We'll just put an ln on each side. And this is nice because now we can bring those powers to the front. I can bring the x minus 2 down, see? Like that. And I can bring the 3x plus 2 down. And I'm going to write a little note here that you need to use parentheses when you do that. You can't just bring it down without keeping it as a unit. So I'm going to put useth parentheses, which is an ancient English way of saying use parentheses. Okay? Very important. Okay. Let's distribute this all out properly. So this would be x ln 5 minus 2 ln 5. And this would be 3x ln 3 plus 2 ln 3. So distribute. And I think we should bring all the x terms to one side. So let's group all x's to the left. So let's write x ln 5 minus 3x ln 3. And there's a 2 ln 5 right here. I don't want that here. Let's put him on the other side. So 2 ln 3 plus 2 ln 5. Now I've got all the x stuff on the left and all the non-x stuff on the right. And now let's factor out an x. And I get x times ln 5 minus 3 ln 3. And then the right side is 2 ln 3 plus 2 ln 5. And I can divide.
Can't you factor out a 2 there at the right table?
I could. I actually could factor out a 2 on the right. My goal is to isolate x. So I'm just going to leave it. If you want to factor out the 2, Matt, go for it. I like this answer. The reason I like it is because all of them are like log of 3 and log of 5 and, you know, prime number stuff. That's nice. But there's another way to write this. I'll let you try it at home. This entire thing could be written as log base 5/27 of 225. You might say, what in the world? How could you write it like that? Well, if you apply your rules of logs, you can rewrite this in an infinite number of ways, as I was saying before. So you could write it as log base 5/27 of 225, which is better. I don't know. This one has nice primes in it. I like that. But then again, it has lots of logs. This is one single clean log answer, but it's got fractions and garbage in it. So which is better? I don't know. They're both good. That's got composite numbers and fractions. This is sort of all cleaned up, but it's expanded, so I'm not sure which is better. Just be flexible. See if you can get that red answer later, okay? All right, and now we're going to go on and look at the last example. And this one has some things in it that I think you need to know for college, so I will make sure to point you in that direction. Even if you take a simple calculus class in college, you'll run into this again. All right. It might be the only time in high school you see it, though, because in my calculus class next year, we probably won't cover it until after the AP test, and that's only if there's time. But it does show up in pre-calc and then later in college calc. Okay, so this problem, I would probably just multiply by 2 first. So let's multiply by 2 on both sides. So now it looks like e to the x plus e to the negative x equals 6. And what's cumbersome about this problem is the fact that there's a positive power and a negative power in the same thing, same problem. So that's no good. So what I'm going to do to fix that is I'm going to multiply both sides by e to the x. So I'm going to multiply this entire equation by e to the x. Why am I doing this? It's because it helps me. Sometimes you just do things because it's helpful to do it. Okay? So watch what happens. If you multiply e to the x times e to the x, so we're distributing now. What's e to the x times e to the x? E to the x squared, or you could put e to the 2x, because you could add the powers. E to the x and e to the x, add the two x's together. So e to the 2x. What's e to the x times e to the negative x? It's e to the 0, right? So here you, basically what I did is I multiplied these together and I added x plus x. And then when I multiplied these together, I added x and negative x. So I get e to the 0. The right side is 6e to the x. So the right side got a little more complicated, but the left side actually cleaned up a little, and I got e to the 2x plus 1 equals 6e to the x. If we bring everything to one side, this problem looks very similar to example 4. Looks like example 4 up above. So we put ourselves in a familiar situation. This is very desirable in math. Anytime you're in a new situation, see if you can put yourself in a familiar situation. I wish this would factor. I tried it earlier and I couldn't get it to work. So unfortunately, I'm just going to have to use the quadratic formula. So it looks like, you know, x squared minus 6x plus 1 equals 0. That's the style of problem it is, you know, it's quadratic sort of, right? The problem is it doesn't really factor. Well, how would you solve x squared minus 6x plus 1 if you couldn't factor? Quadratic formula, right? So we can apply that here. It's just, we're not dealing with x as our variable, we're dealing with what? E to the x. So what occupies the space of your variable is e to the x. So you just sing your song differently. You don't sing x equals negative b plus or minus root of. You sing x equals, you sing e to the x equals negative b. See? So you're just going to use e to the x equals negative b plus or minus square root of b squared, which is 36, minus 4ac, which is 4, all over 2. Okay, so we end up with e to the x is equal to 6 plus or minus 4 root 2 over 2. And if you divide the top two terms by 2, you get 3 plus or minus 2 rad 2. Like that. Is that the final answer? Not quite. This is e to the x. To get x by itself, you can just ln. So it's going to be like this. Here's your final answer in red. X equals ln of 3 plus or minus 2 root 2. Now, I actually knew that this problem would have two solutions. Let me tell you why. Okay? You guys have memorized a lot of graphs. You've memorized all these graphs on my wall and 6 new ones. You've got the 2 to the x, 3 to the x, e to the x, and the 3 logs, right? Well, I happen to know this graph. This is one that I memorized. Okay, this is a very, very important graph. And this graph looks something like this. It's a very important graph in physics and in math. Okay, it's an even function. Okay, so it has y-axis symmetry. It looks kind of like a parabola. It's a little flatter in the middle. Passes right through 0, 1. That's what it looks like. So as soon as I saw this question, my mind went straight to this graph. I was like, okay, I know this graph. And I know y equals 3, of course. Y equals 3 is just a straight line like that. So I already knew there was going to be 2 intersections.
What's the vertex of that graph?
The blue one?
Yeah.
0, 1. Is that right? Yes. Yes, 0, 1. The point is, you should get to the point where you know more and more graphs, right? Well, whenever a graph's important in the field you're studying, you try to memorize that graph as best you can. So this is an important graph, and I can tell you it has 2 solutions. So I'm probably going to need to check my work, because there's my 2 solutions. But I would probably want to make sure that this is positive. This is a log after all. This should be a positive input. But 3 plus 2 root 2 is about 5.8. And 3 minus 2 root 2 is positive. It's just like 0.2. It's close to 0. So I'm comfortable with my answer. And this is very hard to check, so I'm not going to check it. But I trust it. I know there's supposed to be 2 answers to this problem. And I got 2 positive answers, or 2 real answers. So we're good. All right, so that's the end of that. And you guys now